Hello, and welcome to the last video covering topics from section 1.3 of your textbook. In this video, we will revisit the matrix vector product in a new way. We will also discuss the topics of linear combination and row and column picture visualizations of a linear system. Okay, let's revisit that matrix vector product that we saw last time. So in our last video, we said, okay, if you take some n by n matrix A and you think of it in terms of its rows, then you take some m by 1 column vector. So the number of rows in this vector is equal to the number of columns in A. Then the matrix vector product, AX, which, okay, if we write it out as with A in terms of its rows and the vector X, then that is equal to another vector. It is an n-dimensional vector, and the first entry is just the first row of the matrix dotted with your vector. The second entry would be the second row of the matrix dotted with the vector, all the way down to the nth entry of the matrix is the nth row dotted with the vector. Okay, the matrix vector product, thinking of it in this way, we're going to call it the row version of the matrix vector product. But we're going to think of it a different way now. So now let's take some n by n matrix and we'll just write it in general. We'll take some m by 1 column vector. So again, same matrix, same vector. We're just no longer thinking of the matrix in terms of its columns. We're just thinking about it in general. Then, okay, the matrix vector product AX is, all right, it's, kind of a hassle to write down, but this is what we get using the row version. The row definition is, all right, you take the first row dotted with X, that's what you get. Second row dotted with X, that's what you get, and so forth all the way down to the last row, dotted with X gives you this last entry. Okay, so this is all what we've seen before, but now I want to do some manipulation to motivate a different way of defining the matrix vector product. Okay, first thing I'm going to do is notice what I did here is I just separated out the different terms that were showing up in the matrix vector product. So I said, okay, we've got matrix vector product AX. Well, the first term in this sum has an x1 in it. The first term in the second sum has an x1 in it. The first term in the last sum also has an x1 in it. And so I kind of peeled off, say, a whole vector here and made it its own, and then added to it the second terms in all of the sums, and then just keep peeling out these vectors, and then finally you have the last terms in all the sums. Make that its own vector here. And now notice if you really just went back and added all these vectors up, okay, you would get this. So I haven't done anything crazy. I've just rewritten it in a way that I can do, though it's perhaps totally unmotivated at this point. The next thing I'm going to do is I'm going to factor out an x1 from this because I can. So let's do that. Maybe this feels a little bit familiar from writing the vector equation of a solution. So all right, we'll factor out x1s from this column, factor out x2s from this column, factor out xm's from this column. And so we can write the matrix vector product in this way. It's x1 times this column plus x2 times this column of entries, all the way up to xm times this column of entries. And notice that these guys, these are all the columns of A. So all the columns of A are showing up. We're taking, A11, A21, all the way to AN1. There we go. Same here, showing up here and here. And so this gives us another way to think about what we're doing with the matrix vector product is we're saying, okay, if we have some matrix and some column vector, then the matrix vector product, what's going on is we're taking the first column of the matrix and we're scaling it by the first entry. And then we're taking the second column of the matrix and we're scaling it by the second entry, the final column, all the way up to the final column of the matrix, scaling it by the final entry. And that is the sum. And it'll give us the same thing. It's just some algebraic manipulation to get from one to the other. So yeah, let's define this for real, the column version of the matrix vector product. So we have some n by m matrix, but now this matrix, instead of thinking about it in terms of its rows, let's think about it in terms of its columns. So each one of these v sub I columns is going to be a column vector with n components, and that's because there are n rows in this matrix, and there will be m of these columns. Okay, we've got some m by 1 column vector. That's just the same as before. Then the column version of the matrix vector product is as follows. Ax is, all right, just rewriting it in terms of how we're thinking about A in terms of its columns. And the column version of the matrix vector product is as follows. Take the first column vector in the matrix A, scale it by the first entry in the vector, all the way up to the last column in matrix A, scale that by the last entry in your vector. And no, this is still, add these all up, you're going to get a column vector with n components. You'll get a n by 1 column vector. Let's all put a hex on the person who decided that we should have n by m for our matrices instead of like p by q or something where you could easily distinguish what you're saying. Anyway, okay, end rant. But okay, you add these all up and you still get a column vector with n components. And last thing I'll say on this slide is that if you're feeling lazy, you can write it like this, where, all right, you don't bother writing the whole matrix, column vector matrix form of this. You just say, all right, it's x1 times vector v1, and it's understood that this is the column vector. It's a column vector, and it's understood, okay, that's the first column of matrix A. We will write so many of these that you will very quickly be happy to write it like this and save yourself the time. But okay, let's do an example. So last time we calculated a matrix vector product using the row version, and we said, all right, we've got this matrix. It's a 2 by 3 matrix, and multiplying it by 3 by 1 column. And all right, dotting the first row with the first column gives you the first entry. Dotting the second row with the second column gives you the second entry. And we ended up with 11, 1. This is all, I just copied and pasted this from the last slide. That was the row version. Now let's calculate this using the column version of matrix vector multiplication. So we start out, same matrix, same vector. And now remember what we're doing is we're going to take the first column, scale it by 3, the second column, scale it by 1, third column, scale it by 2, and add. And that's just what we've got. And so now, all right, let's just actually do that scaling. This would be 3, 3. This would just be 2, 0. And this would be 6, negative 2. And then adding up the entries, 3 plus 2 is 5, plus 6 is 11. 3 plus 0 is 3, minus 2 is 1. So we get the same thing, which is a relief. And so let's think about the matrix form of a linear system again. This is where we went with this last time when we were talking about the row version. And actually, in one sense, it's the same. Okay, we can write the linear system with augmented matrix as looks like this, meaning coefficient matrix A and the numbers to the right of the equal sign. We put in this vector B. And then, okay, the linear system can be written as matrix A times solution vector X equals constant vector B. But now let's do some manipulation of this with our column version definition of matrix vector product. So AX equals B. If we write A in terms of its columns, and B as a column vector and X as a column vector, then we rewrite that out within the column version of the product, rewrite it as follows. So really, this is just the matrix vector product equals this vector. And because we're often feeling lazy, we will write it like this. Uh, and you might be thoroughly unimpressed with this slide because it's like, well, this is just the last slide, except we tacked this b on there because we said ax equals b. And you, I suppose, are right to feel a little bit grumpy about that. But the reason I did that was because expressions that look like this come up so often that we give them their own name. So we call an expression like this a linear combination. So let me be absolutely precise on the definition of linear combinations because they show up all over the place. I mean, not just in this class, but I use them in my own research. So in fluid dynamics, so it comes up in a lot of places. So let's be careful to define it correctly. So a vector b in Rn. So think of this as a column vector with n components. That vector is called a linear combination of some other set of vectors, v1 to vm, in Rn. So, okay, we have an n-dimensional vector, and we say it's a linear combination of some other group of n-dimensional vectors. Say we have m of them. Okay, so B is a linear combination of these vectors v1 to vm if there exist scalars k1 to km such that, okay, k1 times vector 1 plus all the way up to km times vector m, that if we add these all together, we can get B. And so what this is saying, all right, we've got some vector B. It's a linear combination of these vectors. If we can generate B by just scaling the vectors in the right way and adding them together. And we're going to see this picture in just a moment, and then again and again throughout the term. So before moving on to the picture of this, let me just say one thing. Notice that this is very similar to the definition of a linear equation. Remember, a linear equation was something where you have a bunch of unknowns scaled by a bunch of coefficients is equal to a number. And so in form, these look pretty similar. Like, it's just that the unknowns in the linear equation are replaced by vectors for the linear combination. And the right-hand side, instead of being a constant number, is just a constant vector. And so this is one reason why we call something like this a linear combination, is because it's reminiscent of the linear equation. Okay, now to my favorite part of this lecture, row versus column picture visualization of linear system. Okay, so let's look at let's read this part first. So there are two ways of computing a matrix vector product that we've seen. And now this gives us two ways to visualize a system of linear equations. So let's look at an example. All right, we've got two equations, two unknowns. If we were to write this in matrix form, where we made the AX part, we multiplied it out using the row version, we would get something like this. And the row picture, to visualize the system, well, to get that, you graph the rows, and then the solution is the intersection of the graph. So this row, graphing the rows is, all right, it's the same as just graphing these equations, because the first row is 3x plus y equals 7. Second row is x plus 2y equals 4. So really, this is nothing new. You say, all right, this is essentially graph the equations. The solution is the intersection. So the solution here would be x equals 2, y equals 1. All right, so this is nothing new. Here is the new way of visualizing. Same example, same set of equations, two unknowns. But now let's put it in matrix form, but where we are multiplying the coefficient matrix times the solution vector in the column version. So here, now we're saying, okay, in the column version, we're taking the coefficients of the coefficient vector 3, 1, scaling it by x, the coefficient vector 1, 2, scaling it by y, and saying that, all right, if we scale, if x and y are the right numbers, we can get this vector 7, 4. So here's how you visualize using the column version. Well, first, okay, you start with a graph. But instead of graphing the rows or the equations, you graph the column vectors. So we'll graph this vector 3, 1, this vector 1, 2, and this vector 7, 4. That's what we did. Vector 3, 1, vector 1, 2, vector 7, 4. And I just made the coefficient vectors a different color to indicate that they were the coefficient vectors. All right, next, you make a parallelogram with the coefficient vectors as sides and the constant vector as the corner, like this. And then the next step is to say, okay, well, the solution is how much you need to scale the coefficient vectors so they add to the constant vector. And that's what this parallelogram is doing, is saying, all right, if you make this parallelogram, then, all right, however much you need to scale this side to get here, and however much you need to scale this vector to get this side, those scaling factors are going to be your x and y. So here, we made the parallelogram, and it turned out we needed to scale the vector 3, 1 by 2. And it turns out the parallelogram, we could make it without having to scale this first vector at all. And so 2 times 3, 1 plus 1, 2 gives us this vector 7, 4. And so our solution is x equals 2, y equals 1, just like we got before, but using a different visualization. All right, I think that's enough heavy lifting for one video. I'll see you in the next one.